Oh, hang on. Okay, that's fine. Right, let's get started. So we are AgileRL. So just quickly, kind of what we're going to talk about today. I'll give a quick intro in a second, tell you what we're doing at AgileRL and kind of what the state of AgileRL is. Then I'd like to talk about RLOps and where we see that going in the future, and AgileRL's plans for that. And then I'd like to talk a bit about our future roadmap, opportunities, and then, as you mentioned, we'll leave some time for Q&A at the end. So firstly, hello. We are AgileRL. Param in the audience and I founded AgileRL several months ago, and we did it to democratize access to reinforcement learning, providing human-level AI systems. What does that mean? We believe that the key, or we believe that reinforcement learning is key to any sophisticated AI system of the future. There's all this talk about AGI recently, and we firmly believe that RL will hold a key part of that. But at the moment, it's just really difficult to do. This isn't something that's accessible for a lot of people. The tools are a bit crap, and so that's why we've attacked this space. So just a bit of background. I don't know what everyone's background is, but very quickly, reinforcement learning is a type of machine learning. It's a type of machine learning that learns by optimizing a reward. So we have a model or agent that's placed in a state, and that agent takes an action, arrives at its next state, and it's given a reward for that. And it learns to take the actions that give it the highest reward. And this is a really powerful type of machine learning because it means that we're making decisions, and these agents can plan to make decisions that will benefit them not just now, but also in the future. So some good examples of reinforcement learning that you'll be aware of are ChatGPT is massive at the moment. The main difference between ChatGPT and GPT-3 or GPT-4 even is reinforcement learning. It's been fine-tuned with real feedback, that's been collected online from humans, and that's what's enabled it to be so amazing. Autonomous vehicles are another example of reinforcement learning, where these models are having to make decisions about where to stop, where to go, how to get you to your destination safely. As I mentioned before, though, this is a really difficult technology to master and to use, and it means that it's out of reach for a lot of people. This is because it comes with several challenges and complexities. It's a very complicated paradigm. Some of these things include generalization and the sim to real problem. So often we train our reinforcement learning agents in simulated environments. And then when we want to use them in the real world, we realize actually our simulation isn't that good, or even if it is a very good simulation, there's still things that can happen in the real world that aren't really expected. And the performance of our agent it can decrease massively. Another issue or another challenge of reinforcement learning is reward design. To give an example, I was reading just this week actually on Twitter, some people were freaking out because the US Navy had done a thought experiment. So it wasn't real, but they did a thought experiment where they were trying to teach autonomous drones to kill people, basically. And what the drone would do is it would identify a target, and then it would ask the human controller for permission before executing this person. And what they had done in this thought experiment is they had designed their reward badly, so that the agent figured out that actually, if I kill the human controller first, then I'll have free reign to kill any of these bad guys, I think, whether they're actually bad or not. And so that's an example of reward design gone wrong, and something that as an engineer you need to really think about carefully, especially before you deploy to the real world. But what all these challenges add up to is three big problems. It's extremely expensive. You need to hire expert engineers if you want to do this, and compute costs a lot. Products are so difficult to implement. They have a really long time to value. And as I mentioned, this difficulty has very high barriers to entry. So at AgileRL, we're trying to fix this, and we're trying to streamline this development of reinforcement learning with RLOps tooling. And so where we're starting is with an open source training framework for reinforcement learning that I'll speak about in a bit. But then what we want to do is build this RLOps tooling in a layer above this framework, starting with training, but then moving on to simulation, deployment, and monitoring as well. So where we are now is, as I just mentioned, we have released an open source training framework, which I'd love to tell you about. So here you can see a screenshot of our README, but if you go to this link, you can read all about it and try it out for yourselves. This framework is fully open source. It has online and offline algorithms. And what we've done with this framework is try to create some tools that are much easier to use, less brittle, and ultimately end up with happier engineers that can create reinforcement learning models more easily. What we've done is we've also implemented new evolutionary hyperparameter optimization algorithms that have enabled us to get a massive speed up in training over other libraries that exist, and I'd love to tell you about those as well. So first, let's talk about hyperparameter optimization and why it's such a big thing in reinforcement learning. So hyperparameter optimization is something that every machine engineer has to do, and it's this process of choosing the best hyperparameters that result in a model that learns to do our task best. When you become a machine learning engineer and you think, I'm going to train a model, you think, great, I'll just train it once and I'll get really good performance. But in real life, it's actually a lot more boring than that. And what you end up having to do is loads of trials to figure out these optimal hyperparameters. This is hard enough in supervised learning, but in reinforcement learning, the problem is way harder. And this is for 3 reasons. Firstly, reinforcement learning is more sample inefficient as a paradigm. This means that it takes more updates to our network to get the same improvement in performance. And so every single training run will just take longer. That's just a fact of the algorithms that we use. The next problem with reinforcement learning training is that these learning algorithms are really brittle. And so that means that if our hyperparameters are off, or if our something else is off in the environment, such as the environment being slightly wrong or the reward function being wrong, often our models just won't learn. Unlike in supervised learning, where you'll get your model will learn, but it just won't learn as well. Usually, actually, in reinforcement learning, often nothing happens, and you're left kind of wondering what's gone wrong. The third reason why reinforcement learning hyperparameter optimization is super hard is that, as I mentioned, these algorithms are more complicated. And so the hyperparameter space is much larger as well. And so, there's way more things to optimize. And again, if you have to do all these different trials to optimize all these different hyperparameters, that sample inefficiency is going to hurt you too. So what we've done to solve this problem is we've introduced a new algorithm for evolutionary hyperparameter optimization that is 10 times faster than what can be done with other libraries. And I know that number sounds really crazy, but I'll show you some evidence and I'll explain how it works as well. So the best way to kind of understand how we've managed to do this is to go through a kind of example. So imagine that you're an engineer and you're training a reinforcement learning model, and you're lucky enough to have the compute or the capacity to train 6 models in parallel. So what you might do at the moment is use a Bayesian method. And this is a pretty good method, and it's something that most people actually use at the moment, but it's not great for RL. Not that any method is great for RL. So the way that Bayesian hyperparameter optimization works is you can train 6 different models. So you'll start with 6 different combinations of hyperparameters, and you'll train these models, and then you'll see what the performance is like at the end of that training run. And you can see in this example, the performance bar at the bottom, it's improved, but it's not really quite there. So what you then do is you update your Bayesian model, and then you get more hyperparameters that are more likely to get you a better performance when you train with them. So you do that again, and you get better performance, and then you do this kind of again and again, hundreds or thousands of times sometimes, and eventually you end up with these hyperparameters that give you a really good model. What we've done with AgileRL is in a single training run, we've done that. We've managed to get to that level of performance automatically. How have we done that? with our evolutionary method. So in this single training run, like with the Bayesian one, what we do is we start with 6 models with slightly different hyperparameters, up to the engineer to decide, or you can do it randomly, doesn't really matter. But what we're going to do is periodically, so every 50 epochs or whatever you want to do, we're going to evaluate the performance of those models in midway through training. Then what we do is we use tournament selection, which is just a fancy way of choosing the best ones. And we can have duplicates of the best ones. So you can see there's a couple here that are repeated. That's fine. And then what we do is we mutate those models slightly. We mutate the hyperparameters, but we can also mutate the neural network architectures themselves, as well as actually the parameters of the neural network. But what happens is, without kind of restarting training, unless we've mutated those parameters, we keep those parameters that have that learned semantic knowledge of the environment, and then we continue training. And then again, we periodically evaluate, we do tournament selection, we mutate, and those hyperparameters again evolve to something that is more likely to give us good results. And like with human evolution, because the models that perform best, that have the most appropriate hyperparameters, are more likely to enter the next population through this tournament selection technique, we end up with this population of models that over time evolves, and in a single training run, you end up with really good performance in a population of models. And more importantly, you get this really good performance really quickly. So something I'd like to talk about is how we report metrics for hyperparameter optimization. So as I mentioned, when you're an engineer, you're trying to train your model, you have to do these hyperparameter optimizations, hundreds of times, or sometimes thousands of times. What gets reported in academic papers and journals is not this hundreds and thousands of repeats. What they do is they do all this experimentation, which takes hours, weeks, months, and then when they finally know what those best hyperparameters are, they do a single training run and they record that. But this is not actually representative of the effort we spend as engineers, or of the amount of computation and learning that needs to be done. And so it's not really a fair metric to evaluate performance on for hyperparameter optimization. Instead, what we need to do is see how long it takes to get good performance over the entire number of steps taken in the environment. Because as an engineer, you don't really care if it's how long it takes a single training run to learn. What you actually care about is, if I start training now, at what point in the future will I have a good model? And so that's what we've optimized for here. So along the x-axis on the graph, you can see global steps, and global steps is a count of every single step that is ever taken in the environment to train. And so you can see from these graphs that actually, if you compare global steps and you take into account, the hundreds and thousands of trials versus the single trial that you need for AgileRL to get your algorithm to work, we can get far better performance, not just faster, but also actually higher scores in a lot of cases. And so this is our results compared to Optuna. On the next slide, here's a more visual example, something a little bit more exciting for you maybe. This is the lunar lander environment, and this is our algorithms, our hyperparameter optimization compared to RLLib and Ray. And so in this environment, what our agent is trying to do is trying to learn to land between these flags. And you can see that after just 300,000 steps with our automatic hyperparameter tuning, we've arrived at this model with AgileRL that can actually solve this task. Whereas looking at RLLib, it takes actually millions of steps to get to that same level of performance. So that's where we are now. But where are we going in the future? So I want to talk about RLOps. RLOps is a made-up word, but it really MLOps for reinforcement learning. So MLOps is this set of practices and tools that streamline and optimize the deployment, development, and maintenance of machine learning models. And this can be split into kind of 3 categories. Data orchestration, this is stuff like data lakes, data pipelines. Then we have model orchestration, which is kind of the actual training, testing of models, hyperparameter optimization. all those more fun decisions to make. And then the final, the third section is the code and app orchestration. So this is all about productionizing models, deploying them to the real world, actually using them. The issue here is that the tools and systems that exist for productionizing for these three different sections at the moment are not very good for reinforcement learning. And that's because even though this is called MLOps, machine learning operations, it should really be supervised learning operations, because that is where all the focus has been until now. And there are key differences between supervised learning and reinforcement learning that have to be taken into account when deciding how to do RLOps. So firstly, with data orchestration, there's a big difference between the data that we use for supervised learning and reinforcement learning. In reinforcement learning, often we train in simulations, which is obviously completely different to having labeled data. And often we also have offline data. And sometimes we want to even mix these two together. And so this is a really complicated pipeline and something that has to be approached completely differently to how, having just kind of pretty basic, basic compared to reinforcement learning anyway, labeled data ready to go. The next part is the model orchestration. As I mentioned, these RL algorithms are very different to supervised learning algorithms. They need to learn in environments, they need to act in simulations, so the way that we train them is different. As I've already spoken about as well, the hyperparameter optimization of these algorithms is very different. And also a big issue when it comes to reinforcement learning training is compute. So when we train a supervised learning model, GPUs are king. We want to stuff everything onto a GPU and manipulate our neural networks as quickly as possible. The difference here is that in reinforcement learning, actually, a lot of computation is done on CPUs. And this is because we operate in these simulations, and almost always these simulations have to be run on CPUs. And so what this means is we're constantly moving data backwards and forwards between our CPU for our simulation and our GPU for our updating on neural networks. And so this is actually a big bottleneck and something that hasn't really been solved yet for reinforcement learning. Then finally, it comes to code and app orchestration. What's different about reinforcement learning? Well, as I mentioned before, we have this sim to real problem. If our agent is now put in an environment that's actually quite different to what it's been trained in, it's not going to perform how we want. These environments can be much more, the real world, can be much more dynamic than a simulation. It can have non-stationarity. And so we need to have kind of guardrails around this, and we need to really be careful about how we deploy these models in the real world. Another really good thing about reinforcement learning is the ability to do online training. So, we're talking about this difference between simulation and real world. There is no simulation that is as valuable data-wise as the real world, because that's where the impact matters. So if we can collect data from the real world and use it to update our model and continue improving, that's amazing, that's perfect. And reinforcement learning is a perfect way to do this, where we collect rewards and can train online, but the pipelines need to be there to be able to do that. So what's AgileRL's approach to RLOps? So we've split RLOps into 4 different sections. These are simulation, training, deployment, and monitoring. Simulation, what we want to do is offer quick creation and testing of simulation. We want to offer the ability to integrate offline real-world data into these simulations, almost like populating it with bits of real-world data that's super valuable. And we want to offer better support for reward shaping so that we don't have drones that go around killing our human controllers. The next part that we see is training. So we want to offer fast and stable learning and hyperparameter optimization. And the way that we're delivering this is through our open source framework that I've already spoken about. We want to offer better tools for versioning, organizational support, and visualization as well. The testing that comes around reinforcement learning is different, especially if you're doing offline reinforcement learning and you need some kind of proxy environment. So the way that you evaluate performance needs more support too. And then also I'd like to add that, we want to look at doing optimized compute for RL for the reasons I already spoke about. When it comes to deployment, we want to offer these, really efficient, continuous improvement, continuous deployment pipelines that allow us to take advantage of all this data that we're observing in the real world and make sure that our model is really, continuing to learn from the best data possible, the real world data. We want to allow people to do that online, but also offline if they wish. And as I mentioned before, reintegrate that with the simulation. And then what happens as well, like with all machine learning models, is you have data drift, and in reinforcement learning, you have concept drift, where the kind of environment that you're simulating changes completely. And this could be, if you have a chatbot that you're using for customer service, and suddenly loads of people start complaining because I don't know, it's Christmas time and their deliveries are all late. You need to be able to adapt to those different scenarios that maybe you haven't actually trained for loads and loads of complaints about deliveries. The final part that we see is monitoring. So we want to offer really good observability over these models. These models are super powerful. They can do amazing things like drive cars, but that also means that they're less controllable. And we really need to make sure that they're not making key decisions without kind of proper human oversight. And so that's a really key thing that we're hearing, that people want: better explainability, better oversight. We also want to offer comparison with baselines, things like A/B testing, typical deployment pieces. Now I'd like to talk about the future. So what's our plan for things that we want to release in the future? So in the next half of this year, we're going to keep going with this open source library. We want to introduce distributed compute. This is something that I've been working on very recently. I was actually working on this right before this call. And that's going to be released very, very soon. So you'll be able to take full advantage of any expensive compute that you're lucky to have available to you. We want to keep adding more reinforcement learning algorithms, including multi-agent and hierarchical algorithms. We see multi-agent as a really big space to explore, especially as these algorithms really do suffer from poor hyperparameter optimization, and they're super brittle. So I think this is somewhere that we can really make a big impact. And then we want to keep offering more ability to do different neural network architectures. At the moment, what we've implemented are evolvable MLPs, CNNs, and transformers. We want to expand that and allow people to customize these evolvable networks that mutate with the population in any way they want. And we want to continue to add more and more sophisticated mutations as well. Start of next year, that's when we plan to release our training RLOps tools. So this is the kind of auto HPO tools, the versioning and monitoring I spoke about, and also that optimized compute for RL. Then we want to expand to the other types of RLOps, move horizontally to simulation, deployment, monitoring, and really complete the pipeline so that anyone implementing a reinforcement learning model has all those tools available, and it's super easy to do. Hopefully then we can streamline every impactful AI system. So I hope you've enjoyed this talk. If you'd like to get involved, we would love that. We think the way to do well in this space and actually have people love your tools is to get them involved from the start and get them to help you make them. And so we're going fully hard on open source. We're looking for loads of contributors, so please check that out if there's anything you'd like to add. We also have a Discord channel that's got almost 80 members, so please join. There's a link in the QR code on the screen. And yeah, at the bottom it says we're actually going to start hiring people soon. So if this is something that would be interested in, or someone that's good in this space, we'd love to hear about that as well. Yeah, just please get in touch, contribute if you can, and yeah, thank you very much, and happy to take any questions now. You can email me, my email's at the bottom of the screen.
Perfect. Thank you very much, Nick.
All right.
That was very interesting. Thank you very much. That was very. I have some comments and questions as well, but I'll open the floor. So, Rene, do you want to ask something?
Oops. Yeah, that interesting talk, and yeah, I think RLOps, that's a really good idea. So on the various RL projects that I've done, it's just a huge engineering effort just to get anything up and running.
It is. It is.
I've just got a few questions actually. I wrote down. One is
Sure.
So when you were optimizing the like you said, you optimized it at the same time as you were running the code. I didn't quite understand it because, like you said, you could optimize, for example, also the network structure. But how do you then deal with the weights? Because I mean, if you then change the, let's say you make it a wider network or something, then it's a different network. And how can you continue running on the same? I didn't quite get that.
Yeah, that's a really good question. So you're right in thinking that, hang on, maybe you've added a layer or you've made the layers bigger or whatever, and suddenly you have more or less. Okay, so the easiest example is if you have less. Say you remove a layer.
Yeah,
that's quite simple to think of. You just keep the weights in the other layers.
Yeah.
If you want to add a layer, what we're doing at the moment is we're actually just copying the weights of another layer and then applying Gaussian noise to them. And similarly, when we add other nodes or anything like that, we're copying other ones, adding Gaussian noise, and this is proven effective for learning.
Interesting. Yeah, that's yeah. The other thing is, yeah, you mentioned RLOps. So whenever I've done anything with RL, I've used RLOps because it's just a nice package. And they offer all this, like the scaling up, which is quite useful. All the distributed computing, which I think you're starting to look into now.
Yeah, that's almost out.
Yeah, could you not do a kind of a hybrid where you leverage the ray scaling aspects with your ideas on how to like do the optimization in a more optimal way?
Yeah, so
then you could focus on. Sorry,
it's an interesting approach. The issue that we found with libraries like Ray and RLOps, I mean, kind of the same thing, Ray and RLOps, is that people find them very inflexible. And the way that they created these kind of distributed training frameworks is they've said, right, you know what, it's so complicated, we're just going to do it all in the background. You're going to be given very little control, very little ability to kind of change actually, the minute things that you may want to as an engineer. And it results in this very inflexible framework that is useful until you need to change that one thing. And actually, from loads of conversations that we've had, most people don't really like RLOps for this reason. They like that it's fast, but they don't like that they don't have that flexibility and that control over their learning algorithms, for example. So what we've done is we've approached this from more of a kind of basic kind of PyTorch training loop point of view. You have full observability. We've been using the Hugging Face Accelerate library to implement distributed compute. And this means that without kind of disrupting the distributed nature of the library, you can still change and control every single little bit that you want to.
Mm-hmm. Okay, so basically a much more open approach in a way.
Yeah, exactly.
Yeah, that's interesting. Can I ask one? Sorry.
I was going to ask, how have you found RLOps? Have you not found that,
Well, to be honest, it's the only one that I really know that does anything of that. So,
okay.
So I don't really have any comparison, and I didn't have written my own. So it's like a sample point of one. So, I mean, it's I mean, with RL, there's just so many technical issues that one runs into that I personally never gave it too much thought. I just took it as a given. Just like. One thing that I found is like the gym environment setup. Once you have several people working on it quite a big project, it just turns into a mess. So we actually pulled apart the gym environment and like modularized it, which actually helped just because it made it easy to debug and things like that. And so we didn't even look into we just took RLOps and as a given. Yeah. But
hopefully we can change that.
Pardon?
Hopefully we can change that.
Yeah. One last question on the. So, what that means, you also code up your own algorithms, I guess, like PPO, whatever.
Yeah, that's right. So far we've implemented DQN, DDPG, CQN, which is an offline one, and ILQL, which is an offline one for language. So you can fine tune large language models. But we're planning to add loads. Someone is working on SAC right now. I mean, I've got a whole list that we want to add.
Yeah, because that's actually one. So when we were like on the big project we had, we started off with PPO, and then looked into the SEC that RLib had at that time, which wasn't very good, but luckily we were working with some people from who were actually in Montreal who knew about it, and they implemented their own SEC. And I think last year there was also a paper that often implementation details of algorithms can make a huge difference in how well they work. So it's not, might be some tiny little thing that's not even documented. I think there was a paper 1 or 2 years ago on that. So this is so if when you show these comparisons also then between RLib and yours, but also any other, it's never really obvious to me if it's then the hyperparameters that are different, or if it's something fundamentally just tiny little things in the how they implement the replay buffer, or God knows what, which can have huge effects.
And then the key difference again with our algorithm is that these models are all evolvable. So we have to add, it's not as simple as just kind of calling, I don't know, it's like we could go to stable baselines and just take their version of DQN and then apply that to our hyperparameter optimization framework, because we need to have all these aspects that allow it to be evolvable. And it's not that complicated. I mean, if you go and look, it's just a single file for each algorithm. It's pretty easy to understand, but there's certain functionalities that we need in there for it to work.
Okay, but do you have like a framework where you can make you may make it easy so that people can use other algorithms or try out their own or whatever?
It's super easy. So this, if you look at our documentation, there's literally just a couple of functions that you need to have, and you can kind of like, one of them is like get action or learn. It's like classic kind of RL functions you would expect, but then there's a couple where you need a function that is called clone, and it just makes a copy of the object, and you could literally just go to DQN or any other algorithm and copy that function over if you want. So it's super easy to implement your own version.
Could you do something like where you wrap say stable baselines algorithm in something to make it easier to just port algorithms also?
I think you could, but what you would have to do is replace the neural network that's inside the object to like with one of these evolvable ones, and it's probably not infeasible. It's probably not infeasible, to be honest. I need to look at exactly how how they're even named inside the algorithms and everything.
No, the reason why I'm asking is just because it would then open up a lot of algorithms that are out there, which would be practically immediately.
I mean, it'd be easier than having to write all of them out again as well, wouldn't it?
And compare them, because as I said, it's sometimes tiny little differences actually make a huge effect. Thanks a lot. No
worries. Thank you for coming.
Perfect. Thank you very much, Rane. Any other questions? Any comments from anyone else? No. So I had like one question, but I think it has already been answered regarding the mutations. But I think you've already answered that with the Gaussian noise that you add. You're optimizing, which basically seems to be like the crux of this, like how you kind of in a way like improve the performance of the models. And over there, like
so there's 3 innovations in our hyperparameter optimization that we've done. So the first thing is, well, evolving the hyperparameters has been done before. That's less of an innovation. And I mean, I guess all of them are not really innovations on their own, but it's the combination, the way we've done it, that's novel. So what we've done is we've combined mutating hyperparameters with mutating the networks and the algorithms themselves, and also sharing memory between this population of agents that obviously reduces the number of experiences they have to each individually do, the number of kind of transitions, or whatever you want to call it, that they each have to individually do, because they can learn from what others have observed. Okay. Perfect. And do you plan to do kind of any improvements for this as well? Do you have any ideas? I'm sorry, what did you say? Like, do you plan to kind of take this forward as well? Like any other innovations in this space? Yeah, I mean, we'll keep exploring. At the moment, we're just trying to kind of expand on the framework itself, because there's so many things to be done. I've literally got this massive list next to me. But I mean, look, if there's even more improvements to be had, that'd be amazing. We are looking to hire some kind of top RL engineers to really push the forefront of that as well. Okay, perfect.
So like, if there are no other comments.
Can I ask one follow-up?
Yeah, please.
Yeah. So you said one of the innovations was to share the experiences between the different. I can see how that works with off-policy algorithms, but does it also work with on-policy?
So that's the thing is, obviously that part of the hyperparameter optimization you can't do with on-policy algorithms.
Okay.
So you can do the other two out of the three, and it's still an advantage, but you get the most advantage with off-policy.
Okay, makes sense. Thank you.
Okay, perfect. Thank you. Param, do you want to add anything?
Just unmuting myself. No, nothing for me. I think would love for everyone on this call to join our Discord, get involved. As Nick had mentioned as well, we're looking for contributors. So, if you've got time and you'd want to like dive in, please do. We'd really appreciate it. Any comments as well? Like, I think an interesting one that you mentioned, Mohammed, was, are there any other innovations to be had? And that, because we're building it in the open, we're building it open source. If we welcome those sort of suggestions. So if you've got like an idea of how we can improve on the framework, we would love to hear it. We'd love for you to actually, raise a pull request, get involved, or even speak to us about it and how we can work together to actually improve on it. Because the reason why we're doing it open source is so that we can just accelerate, RL adoption and improve the tooling out there, so that, even if people want to test, because we realize a lot of businesses, prior to getting anything out into production, what they want to do is they want to test. So they want to quickly get a proof of concept out, see if it works, iterate on it. And it's very difficult at the moment, especially for RL. So just by using this open source framework, we want to make it easier, reduce the time it takes to even just test and experiment and see whether RL is a good fit. So yeah, if there's something missing to allow you to even do that test, we'd love to hear about it. We'd love for you to get involved. And yeah, contribute. So we'd love for you to join the Discord, get involved in the conversations as well. That's all I have to add. Nick has done a beautiful presentation. He'll share the PDF as well, so that we can share that across to anyone here. Yeah. And yeah, any comments, we'd love to hear them.
Yeah, thank you all for putting up with me and listening. I've enjoyed talking to you and discussing afterwards. Yeah, as Param mentioned, please share the library around, take a look. We're trying to grow, so anything you can do is super appreciated.
Will do. Thank you very much. Thank you very much, team AgileRL. I think it's a great initiative and a much needed one. There was clearly a gap in this space for a while, and I think I can clearly see like how this can kind of facilitate the developers in this space. I myself am a very firm, even though like reinforcement learning seems to have been kind of a bit at the back foot due to like generative AI and all that, but I am myself a very firm believer of the role of RL in any major breakthrough in AI. Like, I firmly believe that RL is going to be there, and it is there in ChatGPT. So it is still has that thing. So thank you very much again. I think it was very helpful. And I'll share, like, I'll upload the video as well. I'll share that as well. Just roll it out. I will share the link for your GitHub repo as well. And yeah, like we have like next Thursday, we are doing this live live view party of LLMs in production conference, which is happening, like, which is online, but we're doing it over here at UCL. We'll be kind of viewing it over there. There will be pizzas and drinks as well from 3 p.m. till 9 p.m. I'll be like publishing that event like by tomorrow as well, so feel free to join us for that too. And till then, like, see you all hopefully at our next event. Yep,
looking forward to it. Thanks a lot, Mohammed.
Thanks for having us. Bye now.
Bye.